Welcome back to another explainer. Today we're diving straight into something absolutely massive yet completely invisible. We're talking about the plumbing of the internet. You know, that foundational architecture that somehow connects your smartphone, your laptop, and servers sitting halfway across the globe, literally in milliseconds. We all use it every single day, right? But we rarely stop to actually marvel at how this whole shebang really works.
Okay, let's dive into this. Here's our roadmap. We'll start with the Internet's postal system. Then we'll look at getting connected with DHCP. After that, we'll contrast public and private networks, see how we solved a massive address shortage, and finally, meet the Global Internet Coordinator. Let's get to it.
Section 1. The Internet's postal system and the fundamental concept of connectivity.
So, if we think of the Internet as this massive, highly efficient global postal system, how does your phone actually know who it is within that system? Think about it. When you load a web page or send a message, billions of data packets are just flying around the globe. How do they know exactly how to get back to your specific device, whether you're sitting in a crowded coffee shop or just hanging out in your living room?
Well, the answer is the IP address, and it's honestly a dual-purpose masterstroke. It gives your device a unique identity, sure, but it also acts as a precise global location address. That's how those billions of packets find their way back to you. It's exactly like how a mail carrier needs your street address to deliver a package. Devices on a network use this numerical IP address to pinpoint each other and deliver data, perfectly every single time.
Moving to Section 2, getting connected with DHCP, or the invisible handshake. Because man, typing those numbers manually would be tedious.
Now, what's really interesting here is that if we had to manually type unique IP addresses into every single smart TV, tablet, and phone, it would be an absolute nightmare. So enter DHCP, which stands for Dynamic Host Configuration Protocol. The second you connect to a Wi-Fi network, this protocol steps in and automatically hands your device an IP address, a subnet mask, and a gateway address. It acts exactly like an automated post office. It just assigns you a temporary PO box on the network instantly with absolutely zero manual work from you.
And DHCP pulls this off through a lightning-fast four-step conversation known as DORA. First, your device sends out a Discover broadcast. It's basically shouting, "Hey, are there any DHCP servers out there?" The server then replies with an offer, presenting an available IP address. Next, your device sends a request, claiming that specific IP. And finally, the server responds with an ACK, an acknowledgement, officially assigning the lease to your device. This entire DORA handshake happens completely invisibly, literally in mere milliseconds.
Section 3. Public versus private networks, local and global identities. Let's see how your device actually balances these two.
As it turns out, the device you're using right now doesn't just have one IP address. It's actually balancing two different identities at the exact same time. First, you have a private IP. You can think of this kind of like a room number inside a large office building. It gets assigned locally by your router, and it's completely hidden from the outside world. But for global communication, your internet service provider assigns a public IP. That's the street address of the office building itself. And to make these two talk to each other, networks use NAT, or Network Address Translation. It elegantly bridges those hidden internal room numbers with that globally visible street address.
Now, building on that, these IP addresses can be handed out dynamically or statically. Dynamic IPs, which remember are handled by DHCP, are temporary. They change periodically. This makes them incredibly cost-effective and absolutely perfect for home networks. Static IPs, on the other hand, are manually configured. They never change. That makes them essential if you're, say, hosting a web server that needs reliable uptime. But there's a massive caveat here. Because a static IP never moves, it actually makes it a lot easier for bad actors to track and target.
Section 4. Solving the address shortage and rethinking internet scale.
So, as the internet absolutely exploded in popularity, the original system for assigning these addresses ran into a huge logistical nightmare. Just look at the massive gaps in these early network classes. Think about it. If an organization needed to connect, say, 300 computers, a Class C network was just slightly too small since it maxed out at 254 hosts. So what did they have to do? Well, they were forced to use a Class B network, which supports over 65,000 devices. That meant a single company was just sitting on tens of thousands of unused, wasted IP addresses that nobody else could use. Talk about inefficient, right?
So the crucial point is how engineers actually fixed this massive inefficiency. They introduced CIDR, or classless interdomain routing. CIDR uses variable length subnet masking. which basically means instead of those rigid buckets of 254 or 65,000 addresses, CIDR allowed network administrators to slice the IP address space up into flexible, custom-sized subnets. It was this incredibly elegant, necessary rescue of the Internet's infrastructure. It stopped the massive waste of IPs right in its tracks by right-sizing networks to exactly what an organization needed.
But, even with CIDR rescuing the architecture, we still had a fundamental math problem on our hands. The original standard, IPv4, uses a 32-bit address space. It's essentially like throwing a massive party and severely underestimating how many snacks you needed. With billions of smartphones, smart TVs, and IoT devices rapidly coming online, the global supply of IPv4 addresses was completely tapping out. Enter IPv6. This is a massive 128-bit upgrade. Instead of just a few billion addresses, IPv6 offers a supply so scalable, so insanely vast, that it's capable of supporting our exploding digital ecosystem for generations to come.
Okay, Section 5, the Global Internet Coordinator. The overseer, preventing chaos. Who actually keeps this all from falling apart?
Seriously, with billions of IP addresses, those lightning-fast DORA handshakes, static IPs, and the transition to IPv6 happening every single second across international borders, who keeps all of this from descending into total chaos? Well, that massive job belongs to ICANN, the Internet Corporation for Assigned Names and Numbers. They're this decentralized, nonprofit partnership acting as the overseer of the Internet's naming system. They coordinate unique identifiers globally and allocate massive blocks of IP addresses out to regional registries. Crucially, they manage the Domain Name System, or DNS. That's what translates those confusing strings of IP numbers into human-readable names like ICANN.org. They even coordinate the 13 vital root server IP addresses, which basically act as the master directory for the entire Internet. And this brilliantly illustrates a quote from ICANN themselves. They said, "Without that coordination, we wouldn't have one global Internet." And they hit the nail on the head. If different regions started using identical IP addresses or overlapping naming systems, the Internet would just fracture into isolated, completely incompatible islands. It's really this specific, careful global agreement that makes universal connectivity even possible. So, I want to leave you with a thought to ponder. The next time you load a web page or stream a video in mere milliseconds, will you think about the invisible DORA handshake that got you connected, or the public and private NAT routing, or the massive global coordination by ICANN that made that one click possible? It's truly a marvel of human engineering, isn't it? A fragile yet absolutely brilliant unseen plumbing system powering our modern connected world. Thank you so much for joining me for this explainer, and as always, keep staying curious about the systems built all around us.